Hello everyone, I, Professor Rekha Murthy. Today I'm going to explain about the second experiment that is related with the SUMPNER'S test. So the experiment 2 is SUMPNER'S test on a similar transformers and determination of a combined and individual transformer efficiency. What is the aim of this experiment is we need to conduct the SUMPNER'S test on a two identical transformers and to obtain a graph of percentage efficiency versus the load. So before we go with this experiment, we should know why do we conduct the SUMPNER'S test. The alternative name for this test is called as a back-to-back test. Right. So why do we have to conduct the SUMPNER'S test? Though we know the efficiency and the regulation of a transformer can be determined from the OC and SE tests, what we had discussed in the previous session. So that can be determined accurately, but for the determination of temperature rise, it is required that the transformer be put on a full load for a number of hours. So we have to find out the temperature rise. So transformers, if we have for a smaller rating, it can be loaded by means of the lamp loads or by other means. But it is very difficult to arrange a suitable loads for higher ratings of a transformer for purpose of testing. And though the load is arranged in such case, it leads to be a tremendous wastage of electrical energy. Therefore, the SUMPNER'S experiment will help out to calculate the efficiency and the regulation of the transformer. So why do we call this as back-to-back test? That is because one transformer is loaded on the other, so hence it is called to be as the back-to-back test. So the SUMPNER'S test is going to provide the data for determining the regulation, efficiency, and also the heating under the load conditions. And here we are going to make use of the two identical transformers. Both of the transformer will be connected to the supply in such a way that one transformer is loaded on the other. So whatever the power drawn from the supply is that necessary for supplying the iron and copper losses of both of the transformer. So the primary windings of the two transformers will be connected in parallel across a single phase supply. So instead of going with this theory, we can also go with the circuit diagram, then we can understand. Before that, what are the apparatus to be required to connect to rig up a circuit? Let us see that. So we require the ammeter as what we had seen in the OC test, that is 0 to 1 ampere. We require it for which test? Open circuit test, right? In the previous session. And 0 to 10 amperes we required for the short circuit test, 0 to 30 volt we required it for the short circuit test, and 0 to 300 we require it for the OC test. So it's a combination of all this ammeters and voltmeters, the same thing we are repeating here in as what we did for the OC and SC test. What is the difference? The difference, we require an additional voltage, that is voltmeter, that is 0 to 600 volts, which will be connected across the secondaries of the two transformers. And wattmeter, as visual, we require it for LPF wattmeter and the UPF wattmeter. And also and the single phase transformer, that is 2 kVA we are going to use. So we require two identical transformer to conduct this test. So the two number of the transformer is required. Now let's move on with the circuit diagram. So this part, what you can see here, this part of a circuit is nothing but is similar to that of the open circuit test what we had conducted in the first session. But what is the remaining thing here? This is the copy of an open circuit test circuit diagram, and the below one is the almost a copy of the short circuit test circuit diagram. The second thing what we are going to do is that let out, but here we need to connect it the secondary of the next second transformer, so it is back to back test. So S2 which is let out and S2 which is let out from the first transformer and the second transformer, it will be connected to the voltmeter. So that is only the difference. The remaining all what we had done in the OC and DC test, it is almost the same. So here the voltmeter we are going to use 0 to 300 600 volts, and here we are going to connect one SPST switch in between of this, because this SPST switch when it is open, we are going to find out the core loss, that is open circuit test will be conducted, and when the SPST switch is closed, then we can find it will be the short circuit test. Okay, fine. So after that we are going to complete this loop, and also we need to connect the SPST, we need to connect the voltmeter across this SPST switch. Okay, then this also the left out is the primary of a second transformer is also being connected back to back. P1 is also connected back to back and P2 is also connected back to back. So it's a very simple one. We need to combine the two circuits, that is OC test and a short circuit test circuit. Okay, now let's move on with the procedure, how we are going to conduct this experiment. So here, with the SPST switch is kept open, and the auto transformer, make sure the auto transformer is in minimum position and the supply is switched on. Okay, right. Then the polarities of the secondary voltages of a transformer will be checked by making use of the voltmeter which is connected across the SPST switch. So I hope so you can see that this voltmeter, which is of the range of 0 to 600, this voltmeter is just to check the polarities of the secondary voltages. Okay, fine. How to check that? So if the voltmeter indicates 0 reading, then the SPST switch is closed. SPST switch is closed. If the voltmeter reads 0 reading, then we need to close the SPST switch and we can conduct the experiment. If the voltmeter indicates twice the secondary voltage, then the secondary terminals, that is the secondary terminals of any one of the transformer will be interchanged. It will be interchanged to make that voltmeter to read 0. Then only the SPST switch is closed. So we have to make ensure that this voltmeter should read 0 when the SPST switch is open. If it is reading twice the reading, then we have to switch off the supply, and we need to interchange this connections of the secondary windings. Okay. When let's see that the voltmeter is going to read 0, so SPST switch is closed. Now, by operating the auto transformer, the voltage is applied. Now we are going to switch on this. We are going to close the SPST switch, then vary the auto transformer such that the voltage applied to the secondary is increased gradually till they carry the rated current. What is the rated current? 8.7 amperes for 2 kVA transformer, as what we discussed in the previous session. The readings of all the meters will be noted and tabulated. Then we have to bring back the auto transformer to 0 voltage position and open the SPST switch, then the supply switches. So let us move on with this small procedure what we had followed. And this will be the tabular column which are going to tabulate it. So this will be the voltage which you will get it at your the first transformer, the voltmeter which you had connected, and the IoT, this will be the current which is flowing at the open circuit, and this will be the wattmeter, the first wattmeter for first part of a circuit. We need to calculate the K1 and K2 because that is a, what is it? It is a K constant. We have to consider it, and we need to multiply with the watts, how much power we get it. Then this will be the short circuit voltage at the secondary part of your circuit, and this is the current which you are going to keep it as a constant, that is 8.7 ampere, which you are going to keep as a constant. Then we have to note down all these readings. Okay, so since there will be a 2 wattmeter, we need to calculate separately the K1 and K2 constants. Then we will get a total core losses, that is a W0 T, and also the core loss of a one transformer, since we are using a two transformer. So this each transformer core losses of one transformer, let me consider as a Pi, which is equal to W1 by 2, half of it, and total copper loss will be the WSE2, that is W2 wattmeter, second wattmeter, and again the copper loss for a one transformer, that can be given as PC is equal to W2 by 2. Okay. Then the total copper loss, okay, just a minute. This will be the core loss of another transformer, that will be W2 by 2. And the total copper loss will be the another one, that is W1. Okay, so W1 and W2 is giving the total core losses. Then we need to calculate the I0 and V0. I0 will be the I02 divided by 2, and V0 will be the V0 T. And WC will be the WC T divided by 2, and W0, this will be the W0 divided by 2. This will be the results of your the open circuit, and for the short circuit, WSC, VSC, we need to calculate it, from which cos phi naught will be equal to W0 divided by V0 into I0. So where do you substitute these formulas? So these formulas will be substituted in the efficiency formula. So here I can show it. So that is x into kV into cos phi into 10 power of 3 divided by x into kV into 10 power of 3 plus WOC, that is open circuit, the wattmeter readings, plus the x square times of WSC, that is the copper losses of the each of the transformers. Okay. So also we need to calculate the components of the no load current. That is the magnetizing component current, that is I mu is equal to I0 into sin phi naught, and IW will be equal to I0 into cos phi naught. Then the shunt branch reactance X0 will be equal to V0 divided by I mu, and the loss component, that is this is another loss component, and the shunt branch resistance will be the R0 divided by R0 is equal to V0 divided by IW. So whenever you prefer this total impedance, which is referred to the high voltage side, it can be denoted as Z02, which is equal to VSC by ISC. So resistance and impedance can be obtained as what we had done in the previous session. So R02 will be equal to WC divided by ISC square. From this, we can find out the X02. X02 value will be equal to the square root of Z square, Z equivalent square minus R equivalent square. Further, those values will be now utilized to solve the efficiency. So this efficiency will be calculated for a different values of a fraction of a load, that is 0.2, 0.4, 0.6, 0.8 and 1. For the different power factor, it can be 1, 0.8 and 0.6 will be calculated and plotted the graph. So this is what the nature of the graph will be obtained. That is, the y-axis will be the efficiency and x-axis will be the x fraction of the loads. So finally, the result will be the SUMPNER'S test on a similar transformer is conducted, and the combined and individual transformer efficiency will be determined. And also, the graph of the efficiency and the kV output will be drawn for a different values of the power factor. Thank you for watching this video.